This is lab 3 by Ivan Nikobovich. So, part of the introduction, the purpose of this lab is to demonstrate the parallel and perpendicular forces using GlowScript. Essentially, what we did was find the mass of a black hole by analyzing a star's orbit, and then we use this information to find the initial velocity of the ship, and then based on this, we tried to estimate this initial velocity in order to get the ship as close as we could to the black hole without crashing into it and for it to leave the surface. So we know that the parallel component of the force is in the direction of the momentum. We know the perpendicular component of the force is perpendicular to the momentum. So there's two models here. There's right here and over here. This is essentially demonstrating the orbit of the planet. This was the first component of the lab, where we used GlowScript to demonstrate the orbit, and then on the right side, the second component where we demonstrated the path of the ship and how close we can get it to the black hole without it crashing and leaving the planet's surface. So the assumptions we were making that no outside forces on the black hole are acting on the black hole, planet, ship, and system. That universal gravitational force is not constant, so the average velocity will be replaced with final velocity. We know that F-net parallel is the same direction as motion, and that if this changes, then the object is speeding up or slowing down, and then changing F-net changes the direction of the object. So main fundamentals of physical principles, that final velocity was initial velocity plus F-net over mass times delta t. Final position equals initial position plus velocity times delta t. Gravitational force equals negative g times m1 times m2 over r squared, and that according to Newton's second law, that F-net equals to dp over dt, or the change in momentum over time. So brief preview. So we found the mass of the black hole as a result of part 1 of the lab, and we got that it was 2.204 times 10 to the 34th kilograms, and then based on this we made estimations to get the ship as close as we could to the black hole without it crashing, and the velocities we got for the initial speed were, for the x component, negative 5.614 times 10 to the 7th meters per second, and then for the y component, 0.299 times 10 to the 7th meters per second, and then for the velocity, just the magnitude of both these values of 5.6222 times 10 to the 7th meters per second. So the system is the black hole, the ship, and the planet. Surroundings of space. Initial conditions, the planet is orbiting the black hole, and then we also know that time starts at 0 and the black hole is at the origin. So the coding details explained in a clear logical manner. On the left side is part 1 of the lab. Essentially, first we calculated for the initial velocity vector, final velocity vector, initial momentum vector, final momentum vector. Then we got the delta v and delta p, and we solved delta v by v final minus v initial to change velocity, and then change in momentum, which is p final minus p initial. And we know according to the dp dt, just change in momentum over time, which is just delta p over delta t. Newton's second law, the F net equals dp dt, and then we know that then we next calculated the dp dt parallel components. So first we got the fat vector, then we got the d mag dp dt, and then we got the dp dt parallel, which demonstrates the parallel component, dp dt parallel component, and which we just multiply d mag dp dt times fat vector. And according to Newton's second law, we know that f net parallel is equal to dp dt parallel, and then we solve for dp dt perpendicular by subtracting dp dt parallel from dp dt, and then according to Newton's second law, once again, f net perpendicular is equal to dp dt perpendicular, and then we solved for the mass of the black hole by isolating the mass variable in the force of gravity formula, which is negative g times m1 times m2 over r squared, and we isolated this, essentially getting f net times the r squared over the g constant times the mass of the star, and then over here we change these values appropriately to demonstrate the arrows for the f net perp and f net parallel. Over here is the second component of the lab, in which we estimated the velocity for the x and the y. Then we essentially got the position vectors for to the planet, and then we solved for the force, gravitational force, which is just negative g times m1 times m2 over r squared, and we did this several times in different situations. And then here we did the updated velocity formula for the planet, updated position formula for the planet, and then we did the updated velocity for the ship and the updated position for the ship. So the similarities of models. So the similarities is that both black holes are the same, they're both in the same solar system, and both planets are the same, and that the only difference is that in this model that there is a ship leaving the planet, and it is not, and it is getting as close as it can to the black hole. So the potential source of error is coding accuracy, plotting the scales, and rounding values. So what does it mean? You discussed how the net force and its perpendicular components are different from the rate of change in momentum. Okay, so the difference is that the net force demonstrates all the forces that are occurring, potentially the spring force, potentially the drag force, and the difference is that the rate of change in momentum demonstrates what these forces are doing. So F parallel is the net force parallel perpendicular to the direction, parallel to the direction of the motion, so equal d mag over dt times Phys, and the F perp is the net force perpendicular to the direction of motion. And we know that net force is a change of momentum over change of time, so mass times acceleration, and it demonstrates all the forces that are acting on it as opposed to like dp dt. Yeah, so what if, instead of wanting to take a quick look at the black hole and leave, you decide you want to enter an orbit around the black hole? What is the initial velocity the spaceship would black hole? Okay, so when I tried to model this, I could not get an answer. I tried several times and I was unable to. So I could not find a situation where this would work. Thank you, everybody. My name is Village.